Hello, and welcome to this presentation, Configuring Closed-Loop Power Control on the SMW200A. In this short presentation, we'll use an SMW200A to explain how to configure closed-loop power control on Rohde Schwarz analog and vector signal generators. This presentation is divided into two sections. The first is a general technical overview of closed-loop power control and why this is important in many RF applications. The second goes step by step through how to configure closed-loop power control on a Rohde Schwarz SMW200A vector signal generator. Note that although we'll be using the SMW in this presentation, closed-loop power control is implemented and similarly configured on most Rohde Schwarz analog and vector signal generators. Many RF testing scenarios require the generation of highly accurate and highly stable power over a period of time. The required degree of accuracy will vary by application, but accuracy or variation on the order of tenths or even hundredths of a dB is often desirable. Although modern signal generators can easily meet this requirement, the power at the input of the DUT is affected by devices between the generator output and the DUT, such as cables, connectors, amplifiers, etc. Furthermore, the gain or attenuation of these devices may be dependent on frequency, input level, and even temperature. For example, the gain of an amplifier is often a function of all three of these parameters. There are several approaches to this issue. The first is to manually calibrate the signal chain using an RF power sensor. The DUT is temporarily replaced by the sensor in order to determine the appropriate offset to be entered on the generator. The greatest disadvantage of this approach is that it has to be performed every time the frequency or the level of the generator changes. A somewhat more sophisticated approach is something called user correction. Here, the generator uses an attached power sensor to automatically create a table of corrections as a function of frequency. The most important limitation of user correction is that it's performed at a fixed power level, and therefore does not account for any variation in gain or attenuation along the path. Note, too, that both of these approaches involve replacing the DUT with a sensor, and thus neither approach can be used for real-time adjustment during operation. A more efficient and a more accurate method is something called closed-loop power control. Here, a feedback loop is used to monitor and adjust the generator output, with the feedback being provided by an RF power sensor. This sensor is connected to a directional coupler and provides feedback on the received level to the generator. The generator uses this information to change the output power to match a user-specified target level, usually defined as the desired level at the DUT input. Closed-loop power control allows real-time monitoring and adjustment and does not require any special hardware, software, or license on the signal generator. Let's go through this step by step. Here we're using an SMW200A vector signal generator to provide power to a device under test. Our desired signal level, or target level at the DUT, is 0 dBm. An amplifier with a nominal gain of 10 dB is downstream from the SMW, so the SMW output power is set to minus 10 dBm in order to have a level of 0 dBm at the DUT input. Since the gain of this amplifier may change based on frequency, temperature, etc., we implement closed-loop power control by placing a 20 dB directional coupler in the path. An NRP series power sensor is connected to the couple port and is connected to the SMW over USB, LAN, etc. This sensor sends the measured level at the couple port to the generator. By configuring the SMW with the characteristics of the coupler, and any additional offset needed to account for cable loss, etc., the SMW can then dynamically adjust output power to keep the DUT input power stable at 0 dBm. For example, if the amplifier gain were to drop to only 9 dB, the measured sensor level would drop to minus 21 dBm, and the power at the DUT would drop to minus 1 dBm. Based on feedback from the sensor, the generator power would then be increased to minus 9 dBm, and this would return the power at the DUT input to the target value of 0 dBm. This adjustment happens automatically, and the correction typically takes only tens of milliseconds. In the remainder of this presentation, we'll show step by step how to configure closed-loop power control using the SMW200A and an NRP series RF power sensor. On the SMW200A, power control is configured by first clicking on the RF box in the main GUI and then selecting NRP Power Control. Power control is then configured by clicking on the Power Control tab. Note that power control is configured entirely through the SMW's GUI. No external software or a control PC is required. The next step is selecting the power sensor to be used for closed-loop power control, and this is done under the Power Control tab. Attached sensors can be mapped and parameters can be viewed and changed under the Sensor Configuration and Sensor Mapping tabs. Note that this is only possible when power control is in the off state. In this presentation, we won't go into detail of how to attach and map sensors, so please see the SMW documentation if you need more information about connecting and mapping sensors. The power sensor reading is continuously updated in real time, although remember that this value is usually modified by an offset and/or by an S parameter file. We'll discuss this in much more detail in just a few moments. The target level parameter is the desired power level at the DUT input, and this is the power that the SMW will hold constant when closed-loop power control is active. The Take Measurement at Target Level button copies the currently measured sensor value to the target level. Although the sensor power is read continuously, closed-loop power control is only active when the state switch is enabled. Power control can run in two modes. In the default Auto mode, the power control starts automatically and runs continuously, without user intervention. If mode is switched to Single, the Execute Single button appears, which can be used to execute a single power control measurement cycle. Next, we'll look more closely at the role of the directional coupler in closed-loop power control. If we characterize this coupler, we can remove its effect on the power measurement, and the corrected sensor reading will then display the same power as the power seen at the DUT input. An additional offset value can also be added if we need to account for any fixed loss or gain between the coupler output and the DUT. We characterize the coupler in the form of S parameters, measured using a vector network analyzer or VNA, and these S parameters are exported as a standard S2P file. This file is then loaded into the sensor using the free NRP Power Viewer software package. As we'll see over the next few slides, the appropriate S parameter file is selected under the Sensor Configuration tab. Please note that some NRP sensors may not support the import of S parameter files. Let's walk through a few examples. For simplicity, we'll assume that the SMW is directly connected to the coupler input. Remember that in most cases, there would be some variable gain or attenuation between the SMW output and the coupler input. The power sensor is attached to the coupled port. Since here we're using a 20 dB coupler, the level at the power sensor will be 20 dB less than the level at the coupler input. Next, we set the target level to -15 dBm and do not specify the use of an S parameter file. In this case, the sensor would read the target level of -15 dBm when the SMW output is set to +5 dBm, and thus the power at the DUT would also be +5 dBm, assuming a coupler with typically low mainline loss. Even if gain or loss occurred before the coupler, the DUT input power would still be 20 dB higher than the user-configured target power. So in this case, where S parameters are not used, the target power, or power at the DUT input, will not be the same as the user-configured target power. On the other hand, if we do select an S parameter file for the coupler and enable it under sensor configuration, the SMW will adjust its output power to -15 dBm, because the sensor now provides a corrected reading of -15 dBm at this output power level. The DUT input power in this case would also be -15 dBm, which is the same as our user-configured target power. If we were to add gain or loss between the SMW and the coupler input, the SMW would automatically adjust output power so that the power seen at the DUT input would still remain a constant -15 dBm. As we can see from these examples, using S parameters greatly simplifies the configuration of closed-loop power control, since it makes the power at the DUT the same as the user-configured target power. Before we conclude this presentation, let's look at a few additional configuration settings. The interval at which the generator can update output power is called the power control cycle time. This interval is a function of three things. The first is the amount of time it takes the sensor to make a measurement. This in turn depends on the sensor sensitivity and configuration, as well as the power of the measured signal. After measuring the signal, the system then needs some time for internal processing. The delay time parameter simply allows the user to specify an additional delay before the next cycle begins. Note that typical cycle times are on the order of tens of milliseconds. There are also two parameters that can be used to help protect the DUT from excessive power. The catch range parameter specifies the maximum deviation between measured level and the starting generator output level. If the level measured by the sensor would require a correction step that's greater than this catch range, power control will be paused. This helps avoid very large power steps that could potentially overshoot the maximum input power of the DUT. The RF amplitude limit, on the other hand, is a hard limit to generator output power. The control loop will not attempt to increase output power above this value for any reason. This protection limit persists over resets, configuration save and recall operations, and instrument power cycles. Let's end with a brief summary. Closed-loop power control provides a means of maintaining a constant input power level at the device under test. This is possible even if the gain or attenuation in the path between the generator and the DUT changes. Power can be dynamically adjusted in real time many times per second. An NRP series RF power sensor is used to monitor the generator output power by means of a directional coupler. The coupler can be characterized using a VNA, and the resulting S parameters can then be loaded into the power sensor. This simplifies configuration and operation by making the corrected power reading at the sensor the same as the user-specified target power at the DUT. And finally, although this presentation has shown how to configure closed-loop power control on the SMW200A, please note that closed-loop power control is also supported on most other Rohde Schwarz signal generators. This concludes our presentation configuring closed-loop power control on the SMW200A. If you'd like to learn more about power control, signal generation, or signal generators from Rohde Schwarz, please see the links in the video description. Thanks for watching.